Okay, so let's go ahead and work these heat engine problems. And in the first problem, we're told that a steam engine operates at a hot reservoir temperature, the hot steam temperature of 425 degrees Celsius. Its efficiency is 17%, and we're asked to calculate the cold reservoir temperature. Okay, so here's our expression then for the maximum efficiency of a heat engine. So in part A, we are asked to calculate the cold reservoir temperature if the efficiency is 17%. So let's plug those values into our heat engine expression there. 17% is 0.17, and that equals 1 minus the cold reservoir temperature divided by the hot reservoir temperature. Now we're given in the problem 425 degrees Celsius, but to use this expression, everything has to be in kelvins. So we need to convert that 425 into kelvins. So 425 Celsius plus 273 gives you the Kelvin temperature. So 425 plus 273 is 698 Kelvin. Okay, you do a little bit of algebra here, and you find, so you just solve this equation for the cold temperature. And when you do that, you get a cold reservoir temperature of 579 Kelvin. Now you subtract 273 from that to get the Celsius temperature, and you get 306 degrees Celsius. Okay. So that's the cold reservoir temperature. So that's probably just the surrounding temperature of your steam engine then, because it's still going to be fairly warm right around the steam engine. So about 306 degrees Celsius. Okay, now in part B, we are asked to calculate the efficiency if the cold reservoir temperature is 125 degrees Celsius. Oh, I'm sorry, if it's 150 degrees Celsius. If it's 150 degrees Celsius. So the efficiency then, the maximum efficiency of this engine is 1 minus the cold reservoir temperature. So if the cold reservoir temperature is 150 degrees Celsius, we have to add 273 degrees to get the Kelvin temperature to use in this equation. So 150 degrees Celsius plus 273 gives you the number 423 Kelvin for the cold reservoir temperature. Okay? And again, our hot reservoir temperature, the steam temperature, is 698 Kelvin. So the efficiency then, when you do that calculation, you get 0.39. 39% efficient. So by decreasing the temperature from 306 to 150 degrees centigrade, you can significantly enhance the efficiency of the maximum efficiency of your steam engine. Okay, so let's go ahead and work part 2 of this problem. And I need to erase this. Okay. Now, in part A, we're asked to calculate the hot reservoir temperature of a Carnot of one of these engines that it's at maximum efficiency, given a 42% efficiency and a 27 degree Celsius cold reservoir temperature. So let's plug those values in. Our efficiency then, 42%, is 0.42, and that equals 1 minus the cold reservoir temperature. Remember, we need to get it into kelvins. We have 27 degrees Celsius is the cold reservoir temperature. You add 273 to 27, and you get 300 Kelvin. So that's our cold reservoir temperature, and we're asked to find the hot reservoir temperature. Okay, so do a little bit of algebra here. Add this to both sides, subtract this from both sides, and you get 300 divided by the hot temperature is 1 minus 0.42. which is 0.58, which gives the hot reservoir temperature of 517 Kelvin, or in terms of Celsius, that's 244 degrees Celsius. Okay. Now, in part B, we're told this is no longer a maximum efficiency engine. It's one that operates at 70% of maximum efficiency. And that's typically, in the real world, about as good as it gets. Really, if you improve your design to its maximum extent, the best you're going to do is 70% of that maximum efficiency. So we're told then our efficiency is 70% of the maximum efficiency. Okay? But we still want 42% efficiency here. So we just need to solve this equation here. 0.42 is 0.7 times the maximum efficiency. And so that tells you the maximum efficiency of this engine, if it were the most possibly efficient it could be, would be 60%, 0.6. So therefore, we can now use this value up here to figure out what the hot reservoir temperature would be to get this efficiency. So we plug that in here. 0.6, okay, is 1 minus the cold reservoir temperature, which again is 300 divided by the hot reservoir temperature. Okay, you solve this algebraically just like we did up here in part A, and you find that the hot reservoir temperature is 750 Kelvin. Subtract 273 from that to get the Celsius temperature, 477 degrees Celsius. Okay? So significantly hotter than what we originally had the engine. Okay? And so we had to have it this much hotter to make up for the fact that our engine is not nearly as efficient as the maximum possible efficiency of that heat engine.